Okay, listen. I like to revise everything again so that you can understand better. So these are the four atomic properties. They are the sizes of atoms and ions, ionization energy, electron affinity, and electronegativity. Atomic size is the radius of an atom or an ion. Uh, it is the distance between the center of the nucleus and the outermost shell of electrons. As the electrons are very small subatomic particles, and also according to Erwin Schrödinger, it is a wave in a three-dimensional box. And also orbital is a three-dimensional boundary in which the probability of finding the electron is maximum. The exact position of the electron is not at all known. And also the electron is subjected to the influence of one nucleus only when it is isolated. If an atom is found in a cluster, if an atom is found in a bulk, then the electrons are subjected to the influence of the neighboring nuclei. And also, it is not possible to isolate atoms. So, because of these two reasons, that is, by not knowing the exact position of the electron, and also the inability to isolate an atom, one single atom, atomic size is discussed in terms of a covalent radius, van der Waals radius, and ionic radius. So what is covalent radius? It is the one half of the distance between the nuclei of the two covalently bonded atoms of the same element in a molecule. So the first condition, it should be of the same element and it should be covalently bonded. Then if you are able to measure the internuclear distance, which can be measured by X-ray diffraction studies, there are spectroscopic techniques by which you can measure the distance between the nuclei. If you are able to find out the distance between the nuclei of the molecules, then you can very easily find out half the distance, and the half the distance is the covalent radius of a covalent molecule. Now look here, and even here, we are not sure that it is the exact value because our assumption is that the atoms are hard and incompressible materials. And the second assumption we make to measure the covalent radius is that these two spheres are touching each other, but both are not true. But even then, when you calculate the internuclear distance in the hydrogen molecule, it comes around 0.74 angstrom unit. Hence, the covalent radius is 0.74 divided by 2, it is 0.37 angstrom units. Similarly, for carbon and carbon, it is 0.77, and for carbon and hydrogen, when you calculate, it comes around 1.14. And when you try to calculate using the Cc and Ch, it comes again around 0.37 angstrom unit. But when unlike atoms are present, that is heteroatoms are present with the different electronegativities. I have already discussed what is electronegativity. It is the capacity of an atom to attract the shared pair of electrons towards itself in a covalent compound. In such cases, what will happen? The electron density will be shifted towards one particular atom. And apart from the sharing of the electrons, there will be additional electrostatic attraction between the two atoms. And because of the electrostatic attraction, the covalent radius will be shorter. Equal electronegativities, it will be lengthier. When the electronegativities are shorter, electronegativities differences are there, and because of the additional electrostatic attraction between the atoms come closer. Therefore, we are getting a shorter covalent radius. So we can use this formula. The radius between A and B is equal to atomic radius of A and the atomic radius of B minus 0.09 into the difference between the electronegativities. So the first reason to get a shorter covalent radius is the difference in the electronegativities. And the second one is due to additional overlapping of pi orbitals. If you take ethane, the Cc covalent radius is 0.77. In the case of C double bond C, it is 0.67. In the case of carbon triple bond carbon, 0.60. Therefore, when more and more unsaturation is seen, the covalent radius goes on decreasing. It is because of the additional overlapping of the pi orbitals. See, in the case of ethane, all the pi orbitals are hybridized. In the case of ethylene, one pi orbital in each carbon atom is remaining unhybridized. Therefore, that leads to the lateral overlapping to form the pi bond. In the case of acetylene, two p orbitals in each carbon atoms, they undergo overlapping, lateral overlapping. So therefore, two pi bonds are there. So when the number of pi bonds increases, there is additional overlapping is also increasing, and because of the additional overlapping, the bond distance decreases. That is, the atoms are closer. Therefore, the covalent radius is also shorter and shorter in the case of the compounds where more overlapping is found. In the case of covalent radius, it is not a constant value hence, because in homonuclear molecules, it is different. In a heteronuclear molecule, it is a shorter due to the electrostatic attraction. But in the case of saturated and unsaturated compounds, due to the more p orbital overlapping, again they become shorter and shorter. Therefore, we cannot say that it is a constant value, or the covalent radius is a highly reliable constant value. We cannot say. That is why for all the calculations we take only the average radii, which is a useful quantity. In the chemical calculations, we use only the average radii, which is a useful quantity. But in the case of metals, metals normally do not form covalent compounds, but metals form only metal hydrides and organometallic compounds. So these are metal hydrides and organometallic compounds are examples for metals forming covalent compounds. But other than that, metals form metallic bonds, where the metal nuclei are embedded in a free electron gas. Later on, we will discuss what is this free electron gas theory. And in a free electron gas, the metal nuclei are embedded. In such cases, we can be sure that the metal atoms touch each other and they form a very solid substance. Therefore, weight divided by volume will give you the density. Therefore, if you know the density of the metal and the weight, you can very easily calculate the volume of the metal, and from the volume, by knowing the number of atoms constitute that particular metal piece, and you can find out the radius of an atom. Therefore, this radius is called a metallic radius. Normally, so far, the metallic radius and the covalent radius are calculated. They have not caused much deviation. They are not much deviated from each other. Therefore, the covalent radius is an accepted quantity in chemistry. And this covalent radius is one of the dimensions of the atomic size. And next we will say what is van der Waals radius. And then we will say what is ionic radius. And then we will say how these things are changing when we move along the period and down the group. I think it is time we have to stop. And